In this video, we look into the underlying reasons for why ions of a certain charge form, and we look at the relationship between the size of an ion relative to its parent atom. Earlier in this video series, we learnt that cations, positively charged ions, are formed from metals where the metal tends to lose enough electrons to attain the same number and arrangement of electrons as the noble gas immediately preceding it in the periodic table. We further learnt that anions, which are negatively charged ions, are formed from nonmetals where the nonmetal tends to gain enough electrons to attain the same number and arrangement of electrons as the noble gas immediately following it on the periodic table. For example, from this table we can see that the removal of inner or core electrons from atoms costs a large amount of energy compared to the removal of valence electrons. We can therefore predict that loss of electrons to form cations will only involve valence electrons, and that the number of electrons lost will be determined by the stability of the resulting electron configuration. We know that noble gas electron configurations are very stable since they are non-reactive and form very few stable compounds. In the case of positively charged cations, metallic elements tend to lose one or more electrons to achieve the electron configuration of the noble gas immediately preceding it in the periodic table. For example, metals in group 1A, 2A, and 3A will lose 1, 2, and 3 electrons respectively to achieve a noble gas configuration, and the energies required to do this are not too large. By the time we get to groups 4A, 5A, and 6A, we can see that the energy required to lose enough electrons to gain a noble gas configuration start to get prohibitively high, and we tend not to see cations formed from elements in these groups. This explains why it is only metals that tend to form cations easily. So, in summary for cations, loss of electrons to form cations will only involve valence electrons. The number of electrons lost will be determined by the stability of the resulting electron configuration. Noble gas electron configurations are very stable, and consequently elements tend to form ions that have full electron shells and full subshells in the same way that noble gases do. So for example, for magnesium, it will lose 2 electrons because by losing 2 electrons, it will be transformed from an electron configuration with a valence shell configuration of 3s2 to one with a valence shell configuration of the noble gas neon. For anions, elements with high electron affinity are more likely to form stable anions. The number of electrons gained by an atom will depend on the stability of the resulting electron configuration. Again, the formation of a noble gas configuration is favoured. So, for sulfur, it will gain 2 electrons because by gaining 2 electrons, it will be transformed from an electron configuration with a valence shell configuration of 3s2, 3p4 to one with a valence shell configuration of a noble gas, 3s2, 3p6, which in this case is the configuration for argon. While these general rules apply to many main group elements, it is more difficult to apply general rules to elements in other parts of the periodic table, such as the D block. Aside from full electron shells or full subshells, stable electron configurations are also obtained with half-full subshells. So ions that result in half-filled subshells will also be stable, and this can also be used as a guide to predicting which stable ions may form, particularly in this part of the periodic table. Another property that a consideration of electron configurations can explain is the relative sizes of ions. Cations are smaller than the neutral atoms from which they are derived. This is because removal of one or more valence electrons decreases the electron-electron repulsion, and the outer orbitals can therefore shrink. Removal of all the valence electrons leaves the outer orbitals completely empty, and the size of the ion is therefore determined by the size of the core orbitals, which exist in a shell with a lower value of n compared to the neutral atom. In the case of anions, they are always larger than the neutral atoms from which they are derived, and this is because addition of electrons into the valence shell increases electron-electron repulsion, and this gives the electrons higher energy, which leads to an increase in the size of the outermost orbitals. So in summary, cations are smaller than the parent atom, anions are larger than the parent atom. And this diagram here shows the extent of difference between the ions and their parent atoms for some common main group elements.